I would like to I'd like to call you guys back into the class. Please, whatever you're doing, stop and pay total attention. Before we move into the wave theory, let's take life examples of wave. What do you think when we say the word wave? Alright, so what are the life examples? Alright, so what are the life examples of waves? When you hear the word wave, what comes to your mind? Yes, anybody? Ideas? Like I said earlier, I want it to be an interactive class. Yes, so any ideas? When you hear the word wave, what comes to your mind? That's not what comes to your mind. That's not what comes to your mind. Okay, ocean. How many of you have been to the beach? Don't lie. Yeah, which beach? Which beach? Badagry side. Okay. You, which beach? Which beach? Bad beach. Alright, so whenever you get to the beach, you see the waves on the water. It's usually like this. Something like this. Something like this. You cannot see that the water is what is settled. You cannot see that it is settled like this, like a flowing stream or river. Do you get that now? But you see, you notice something like this, especially when they put big stones at the tip of the, let's say at the river bank, at the bank. So they put stones like this, so the waves will come, hit the stone, then go back. You get something like that. So whenever we talk about wave, what should come to your mind is water, or let's say large body of water, which is ocean, like you said the other time. Sure you get. So most of the times these oceans, they are not what? They are not stable. Sure you get. That's why we have something like ocean current and ocean waves. Do you get that now? So we have ocean. From real life example, we have ocean waves / current. Sure you get now. So now going to physics itself. Going to physics. Now we are moving from real life back into what? Physics. Do you get that now? So now for physics, wave is the transfer of energy. You know what makes this how will I put it? What allows the top of this water to be like this is as a result of a force or a driving energy. Sure you get, of the movement of the water. Are you getting it now? So for wave now, it is the transfer of energy from one medium to another. Are you getting it now? From one medium to another without any permanent displacement of the medium itself. So that is what wave is in physics. Without any permanent displacement of the medium. Now, if we want to cite another life example, if we bring a bowl, someone should get us a bowl and maybe one stone. I know we rejoice. Pass, Joe. I should be a cool. I see it.
Oh, the syllables are carried buckets.
It's like in the video like this.
Should there be water in it?
Yes.
So, no, it's going.
Yeah, feed this with water. Be fast.
We need to look for book.
So you cannot come in here.
Somebody that's sort of asked students.
So this is entry like this.
Like education.
Please say your mouth first. I said that was like that.
Water.
Don't turn it too much so that you don't spoil it. Network is stable. Because of the network, Jerry. Let me put it in DMG. Please play this. I'll go say him. Tabati bikini, tabati bikuru na wanda pada. No, the water is settled, right?
Now, look at. I want you guys. Sorry, come on. Observe something. In the laboratory. Hello. In the laboratory, the things in which they create and that means it's through the use of tank. I want you guys to say that. Usually come out as objective question. Propagation of wave in the laboratory is done through what? So.
Propagation of wave in the laboratory is done through ripple tank.
So now the basic concept behind the tank is this that I want to show you. So now, look at the surface of the water. It is very what? Stable, right? Hello. The surface of the water is what? Yes. It's very stable. So any little touch, are you saying something like this is formed? Something like this is formed. Do you notice that? Let me dig in. So now, on the water, if you have a clear side view, it will look like this. If you look at it from the side, on the water, it will look like it's going like this, like this. Are you getting it now? But from the top, it is like this. Are you getting it now? So now, through that process, the waves are being created or formed. Are you getting it now? In some textbooks, you can just say you throw a stone in the middle to create the ripple. But most times you just create something like this to disturb the water. Are you getting it now? So that's what I have to show you. You can get rid of this. Let's have one. So now the difference between this one that is being formed at the surface of the water is called what? Ripple. It's called what? The ripple. The difference between the wave and the ripple is that one has irregular frequency while one has irregular frequency. The wave now has a very regular frequency, while the ripple has what? Irregular what? frequency. Now, and this is based on the medium or the energy, the medium or the force through which the energy is being what? Transferred. Are you getting it now? Like when I hit the bowl the other time, the energy is transferred from the what? From the bowl to the what? To the water. Are you getting it now?
Yes, sir.
From the bowl to the water. Are you getting it now? So now we are moving to classifications of waves. Where is the duster? Classifications of waves. Is that your bag?
No.
So classification of waves. Now in most textbooks, there are ways in which they classify it, and they use that to confuse even the students that are reading. Are you getting it now? But over the years, I've devised a means in which I classify the waves, and that makes me understand much more better. And when did I discover this? I think that was 2016 or 2017. And I was about writing like. So what I'm trying to bring out is that there are sometimes the information in which you get in textbooks, it is harder to break down. Are you getting it now? You use several means or several methods. You can devise how will I put it? You can derive your own method for easier understanding. Are you getting it now? Like the students I taught last year for physics, they were telling me that they have read classifications of wave over and over and over again. To get to a point, it will be mixed up. Are you getting it now? They don't know how to differentiate some certain waves. So, but I'll make that one easier and lessen your burden on this. Okay. Types of or classifications of wave. For the classification of waves, I make use of two formats. One, I say we classify based on medium of propagation. Based on medium of propagation. What do I mean by the word propagation? Yes? What do I mean by propagation?
Like an object used to form the wave.
Propagation. Propagation means to produce, to make. Are you getting it now? But that's what they use when it comes to wave. Propagation. Do you get it now? They don't use the word produce to produce a wave. They make use of what? Propagation. So don't let it look like a very big word. Do you get it now? It also means to what? To produce. Are you getting me? So now, the first one, based on what? Medium of propagation. That means the medium through which the waves are being what? Produced. That's the first one. Then the second one is what? Based on direction of travel. Waves can travel in different patterns. Are you getting it now? So these are the two major ways I use to classify waves. Are you getting it now? But in your textbook you won't see it like this. So now let's talk on the first one. Based on medium of propagation. Based on medium of propagation. Based on medium of propagation, we have the first one to be electromagnetic waves. electromagnetic wave. We have electromagnetic waves, and two, we have mechanical waves. Mechanical waves. So when you hear of the word electromagnetic, what comes to your mind? Yes? When you hear the word electromagnetic, looks like I saw electric field and magnetic field. No idea. No idea. Production of electric current or voltage. Is that it? This lady has an idea. She's just saying, she's just allowing you to say whatever you want to say. All right. When we talk about electromagnetic waves, they are waves that have been produced without the requirement of any medium. It does not require what? Any medium. You can put that down. These are waves that do not require material medium for its propagation. These are waves that do not require material medium, no material medium for its propagation. All these things, you guys should read it. Next class, I'll ask questions. And once you don't answer, you stand throughout the class. Or you do assistant teacher. So, for electromagnetic waves, they travel through what? Through vacuum. They travel through vacuum. They travel through from the word electromagnetic vacuum. What does this vacuum mean? In a real life scenario, what does it mean? Thank you, space. Outer space. Do you get that now? So most particles that are electromagnetic in nature are from space. Do you guys agree? Do you guys agree? I say most particles that are electromagnetic in nature, they are from outer space. Do you guys agree? Because one major property of electromagnetic wave is that what? They can travel through vacuum. Even during their propagation in the laboratory. Do you get that now? They tend to travel through vacuum. Empty space. Is there any question so far? Any questions so far? Do we understand everything I've been talking about? What of the other guy?
There's no coding.
Alright. Okay, another property they possess is that they can travel with the constant speed of light. They travel at constant speed of light. They travel at constant speed of light. What's speed of light?
Velocity.
Yes, what's the value?
33.8. 3.8.
Yes, value Speed of light. Speed of light. Speed of light. JAMBites. There are some numbers you should not forget. Don't worry, this is our first class. Don't worry. I'll be chipping it in, and as we go, I'll be asking the question constantly in class. So the value for speed of light is 3.0 times 10 raised to the power 8 meter per second. If you should forget that in the next class, that means you are not ready for JAMB. So all electromagnetic waves travel at a constant speed of light. So examples of electromagnetic waves. Examples, yes. Examples. I've even given you guys a score.
Sound.
Light.
Thank you, lights. I say they travel at a constant speed of light, and you know how light is also a type of wave. Do you get that now? Even before we even start the class at all, I've told you guys that optics is under waves, Abi. And what is optics? Optics is light, Abi. So examples, we have light waves. Light wave, radio waves, gamma rays, X-ray, then microwaves. So those are examples of electromagnetic waves. Now, we use another cite another example. How does light wave travel through space? Anybody? It's a simple thing now. You all did geography, Abi?
Yep. I don't do geography.
You did not do geography.
Yes, sir.
Alright. This is the sun. Then we have Earth somewhere around here. Now the sun emits the light. Are you getting it now? Then it gets to what? It gets to the Earth and travels across the space. This is the space, which is a typical example of what? Vacuum. Do you understand the scenario now? That is why it is what? Electromagnetic in nature. Do you get it? It's quite simple. Yes?
Is it because it travels through space? That's why it does it.
Yes.
Have fun.
Understand? Alright. The next one, mechanical waves. Let's talk about mechanical waves. Mechanical waves. These are waves. Mechanical waves. These are waves that require material medium. These are waves that require material medium. For their propagation. These are waves that require material medium for their propagation. And by so doing, they cannot travel through vacuum. They cannot travel through vacuum. And they also travel at different speed. They also travel at what? Different speed. So that's solar emission now. do you think it is only the light that comes into the earth? Yes. Do you think it is only the light that comes into the earth? Yeah, there are some parts of the earth in which they'll tell you not to, by so time of the day, you are not allowed to walk without a clothes that have full covering. If not, you'll be exposed to skin cancer and the like. Do you know? There are some parts of the earth that are closer to the sun than we are. You know, the earth is spherical in shape now, Abin. So there are some parts of the earth. There are some parts of the earth that are closer to the what? To the sun. Do you get that now? Than we are in Nigeria. Do you get that? So the closer you are to the sun, the more exposed you are to whatever is coming alongside with light. Are you getting it now? All these other waves that we mentioned with what is it called? That we mentioned with light wave, they are also emitted from the sun. They travel together. Remember, I said they travel at constant speed of what? Of light. Do you get that now? So most of those waves cause how will let me say they cause health issues. So don't let us go into that. So by saying that, I've established the fact that all the wave travels what? At constant speed. Do you get that now? But this mechanical wave now, they travel at what? At different speed. And they can be either progressive slash traveling. Can be either progressive, that is traveling, or stationary slash standing. Either progressive or traveling, then stationary slash standing. Are you guys with me now? So they can be of these two nature. The mechanical waves that requires material medium. Now, okay, let me take us back to the first thing we did before we started the wave theory. We brought a bowl filled with water. Now, I hit the bowl, that's I applied force on it. Then it's created what? The wave on the surface of the water. Abi? Now, that kind of wave is what? Is it progressive or stationary? How is it progressive? Is it progressive or stationary? Is it traveling or standing?
It's traveling.
How is it traveling?
Because when you applied for the wind, it was traveling.
Now, look at the ocean wave I used to explain earlier. Is that one stationary or traveling?
It's traveling.
Traveling. And the one inside a bowl is also traveling.
Oh, it's stationary.
I hope you guys get it now. The one in the bowl is what? Is standing. Irrespective of the fact that you apply force to it. Do you get it now? It is what? It is stationary. It is standing. But the one in the ocean, so it is what? It is continuous. It is what? Traveling. But the one that is inside just one bowl, it is what? It is standing or stationary. Do you guys get that now? And that one requires what? Its propagation. It requires me to what? To apply the force on the bowl before the what? You can see the wave. Do you get that now? Hello? Do we understand that now? So an example of mechanical wave is what? Water wave. Please take note. An example of mechanical wave is what? Water wave. Are we together? Is there any question? You, do you have any question? You know you are the smallest in this class. Ask question. If you don't understand, ask question. Exactly. All right. Okay, let's eat it on something. There's usually what? Vibration on the prongs. Vibration on the prongs. So now, if you should move that prong to maybe a metal, another metal, you hear a very sharp sound. Do you get that? Can you guys relate to what I'm saying?
Yes.
Like this now, it is metallic in nature. Then this now, maybe you pick it, then eat it on something. You eat it on something, it causes what? Vibration on the prongs. Are you getting it now?
Yes.
Then you put it close to a metal. Then so that is another way of what? Of propagating wave in the what? In the laboratory. And that is what? Sound wave, which is another example of mechanical wave. Are we together?
Yeah.
So another one is waves in strings. Waves in strings. Waves in strings. Waves in string. It's not spring, string. String.
It's
I'm seeing Q here.
T.
Ah. Please, let me look at that. Is that how Q?
Hello, that is Q now.
It's S.
So waves in what? String. Waves in string. Waves in string. Waves in string. What do I mean by string? Yes?
That's like elastic like
That look like elastic. Wow. Please, I don't want any feminine answer. Males, please, answer me. String. String. Thank you. Thank you.
You shall understand.
String, not spring.
Okay.
Spring is different.
Oh.
Spring is that metallic one that used to bounce like this. But string is different. Females, you know of your pants is G-string.
G-string.
G-string. You don't know the real meaning of what you are putting on. Whenever you are talking about string now, let's just don't let us go into this. Whenever you are talking about string now, it means rope. Rope. Open. It means what? Rope. Are you getting it now? I know people want me to dwell more on the G string. So the rope now is another name for what? String. Can we get any rope? Any rope?
Like rubber.
Any rope. Okay, look at this now. Hello. Please pay attention. This is one rope now.
Which one is complete?
Hello. No, don't shift. This is one rope. Hello, pay attention. No. This is one rope. If you look at this now. This now is what?
This again.
This now. You know this rope is tied to this part. Come in. Let's tie this rope to this side. Just doing this so that you guys can understand. Now, this rope is tied.
Hey, hello.
You do something like this. Now, this is a wave. I'm coming. Let me draw something like that on the board. We are still coming to based on direction of travel. Put that in mind. We are still on based on what?
Medium of propagation.
Medium of propagation. Now, this is the string that we, let's say this is the pole. Hello, this is the pole. This is the pole. Now, the rope. This is the rope. Let's say we tied the rope to it. Then we created something like this. Are you seeing it now? Hello. This was what the rope was making. Are you getting it now? Then remember your Cartesian plane. Hello, mathematics lovers. Are you here?
Yes, sir.
Rejoice, you don't like mathematics.
I'm not doing maths.
Hey!
I don't like it. Once I
How
like
come
it,
you are in science class?
even if I don't know.
Jeez.
Young man,
For the mistake.
So, hello, remember your graph, XY plane. Abi?
Yes, sir.
Now you have something like this. Sorry, someone should feel this. You have something like this. X, which one is what? This is Y axis.
Horizontal is the Y, is the X.
Then this is what? X axis. Are you getting it now? Now, hello, please pay attention. This is where the whole thing becomes more complex. Now, we tie the rope to a pole to create a wave. Getting it now? Then we assume that point is the what? Is the point of origin. Then we go like this and like this. This is a wave. So this point now can be our imaginary what? X axis. Which is what? Is it horizontal or vertical? Which is what? Our horizontal plane. Are you with me now? There's a main reason why I am drawing this. Make sure you what? You draw this down. Then you label it. Waves in what? In string. Waves in what? In string. Waves in string. Then the last example. The last example. The last example is waves in pipes.
That's my own being like.
Waves in pipes. The last example under mechanical wave is waves in pipe. Waves in pipe.
Praise the Lord of Jesus.
Wait, in pipe.
Yes, waves in pipe.
Spoil it too.
You cannot do so. It's existing.
Waves in pipe. Now we are moving to the second aspect. Based on what?
Based on medium of
Direction
of travel.
Thank you. Based on direction of travel, medium of travel. Based on what? Direction of travel. Based on direction of travel, we have two types. The first one is the transverse way.
I don't understand it. Should we just spoke about waves and pipe? I thought wanted to talk about waves and pipe.
Yeah, you know, like this.
I said waves in pipe is an example of mechanical wave.
Oh!
Sir.
If you see this section, if you get this,
So the first one is transverse wave.
Based on direction.
The first one is transverse wave. Transverse wave. Then the second one is longitudinal. Longitudinal wave. So let's talk about the first one, transverse wave. Are we on the same page now? All right, transverse waves. These are waves that travel in the same direction Okay, these are waves that travel in the same direction as that of the propagation of the wave particle or medium. They travel in the same direction as that of the
Propagation
of the wave particle. That is, they travel parallel. They travel parallel. They travel parallel. Parallel.
the travel parallel.
Yes. Full stop. A wave is said to be transverse. A wave is said to be transverse. Wait. What did I give you just now? I said
A wave is said to be transverse.
no. Wait. Before that one. This one. AS.
No, when I'm reading it down.
Change that.
Same direction.
They travel perpendicularly, not parallel, perpendicular. They travel perpendicularly. They travel perpendicularly, not parallel. So it is not the same. Instead of that same now, you put they travel at right angle. They travel at right angle as the direction. They travel at right angle. The same. Travel at right angle. Just cancel this one, and this one. Put at right angle. Okay, I said a wave is said to be transverse if the direction. A wave is said to be transverse if the direction of vibration if the direction of vibration or propagation, if the direction of vibration or propagation is perpendicular to that which it travels. That which it travels. Full stop. Transverse waves. Now we'll go back to that practical example we did the other time. Transverse wave has two distinct regions. Transverse wave has two distinct regions. Which are one, the crest. Two, the trough. One, the crest, and two, the trough. The trough, crest and trough. So this is the crest. This position, hello. That practical we did the other time. This position is the what? Is the crest, and this position is the what? Trough. This is another what? Crest, and this is another trough. This is another what? Crest, and this is another trough. So these are the two distinct regions in a what? In a transverse wave. Is there any question? So you have to draw this one again, but you won't draw it like this, you draw it like this. You just put y plane and x plane. Y plane and x plane. So the crest and the trough are two distinct regions in a transverse wave. Is there any questions so far? Are we on the same page? Now let me give you definition of the crest and trough. For the crest, this is the highest upward point of displacement. Crest. Let's talk about the crest now. This is the highest upward point of displacement. Highest upward point of displacement of the wave. From rest position. What did I tell you guys the other time? This point is the what? On your normal graph, it will be the what? The origin, which is 0,0. But for your wave, it is what? It is the rest point or mean point. You can call it mean point also. Mean point. And that is what? 0. And that is 0. Is there any question? For the trough now. This is the highest downward point of displacement. This is the highest downward point of displacement of the wave. From the mean or rest position. Mean or rest position. So examples of transverse waves now. Yes, give me examples. Examples of transverse waves from what we have discussed so far. Examples of transverse waves include it's not me that teach you down. Is X-ray a transverse wave?
No, electromagnetic.
Is it a transverse wave?
Sound.
No, sir.
No, sir.
Why is it not?
Because
Chica, why is
electromagnetic.
it not?
And if it's electromagnetic,
Is it
does
like
that
this?
mean it is not transverse? Yeah, you must answer the questions why in physics. If you really want to know it, you must ask yourself why. Why is this thing like this? Why is this thing like this? She's correct. X-ray is an example of transverse. But why is it an example of transverse? No answer. First assignment.
They are perpendicular. And they travel perpendicular.
How do they travel perpendicularly? The first assignment. Why are electromagnetic waves transverse in nature? That's how I used to give assignment.
Why?
Why are electromagnetic waves transverse in nature? The first example I was expecting you guys to give me is this one. Which one is this one? Where is the string? I said you guys should draw it down and hold it with your left hand. We're coming back to it. This is why we are coming back to it, because it is what? A transverse wave. Yes.
Okay, it's because it's going like this.
Yeah, it's because it's going like this. Look at this now. It travels like this and like this, forming what? Angle what? Angle 90. When you say something travels perpendicularly, what does it mean? Right angle, Abi?
Yes, sir.
Abi?
Yes, sir.
And that is what? Angle 90. Do you get that now? So, waves in strings are example of transverse waves. Then another one is water wave that we discussed earlier. Water waves. Remember I said if you should look at those ripples from one side, it will look like this. So they also travel perpendicularly at what? Angle 90. Then radio waves, which is an example of electromagnetic wave. Just write all electromagnetic waves are transverse in nature. all electromagnetic waves are transverse in nature. Longitudinal wave. Longitudinal wave. Can I rub this up?
Yeah.
All right. Longitudinal waves. Longitudinal waves. A wave is said to be longitudinal. A wave is said to be longitudinal if the direction longitudinal waves.
Are you done? Are you done with all your other courses?
A wave is said to be longitudinal if the direction at which it travels is the same or similar in direction of vibration. Of the wave particles or medium. Just like we said in the transverse wave, that transverse wave has two distinct regions. What are they? Oh yeah, now. First, and you have to open your book and go and check again. All right, longitudinal waves has two distinct regions also. We have the compression region. First one, compression region. Then two, we have something we call refraction.
Let me check what you said. Because what I was saying was matched.
Compression and refraction. Now, instead of string, we'll be making use of what? Spring. Thank you. So there's something we call compression and refraction. So assuming the string is like this, so the point now this point in which they are clustered together is the what? Is the compression. While the point whereby they are not clustered together is the what? Is the refraction. And this is another compression. Let's use straight lines. If you have it in straight lines, we have something like this as the compression region, then this refraction, then another compression, then another refraction, another compression too. So this is compression region, refraction region, compression, refraction, and compression. Should we use the spring as example? Anybody with spring here? But we all have idea of what the spring is having. That metallic stuff that used to bounce like this.
Inside pen.
Yeah, the inside pen, good. Those days we used to buy those pens.
Put down to this.
So now, if we should compress it, it will look just like this, having, in which there's no space. But if we should spread it, it will look like this. There will be space in between. So there are some. If you have a wave on that part, on that type of, what is it called? On that type of object. Are you getting it now? These are the only two region you have, which are the compression and the refraction. Let's talk about okay, let's put something down. In the compression region, is there any question? Ask questions though.
Can we classify? You know, there's one instrument like that. They used to play like. You know, this instrument classify it as why? But it's going the same direction. It's
I know that instrument.
it's compressing and it's flattening, so can't be.
No, you know what? The instrument now, if you should squeeze the bottom will compress, while the top will refract. Are you getting it now? But for this one now, there must be total compression and total refraction. Do you get it now?
It's like they're playing the instrument.
If you compress the bottom like this, the top will spread, Abby.
Yes.
Then if you go back like this, the bottom will
It's not every
spread.
time that they used to play it like this and like this. They play it like this also.
Yes, what I'm trying to say is that for a wave to completely happen in that kind of instrument, there must be total compression and total refraction. Do you get it? Is there any question? So that would distinct the two regions of the wave. Are you getting it now? Is there any question? I said in the compression region, the air pressure is a little above normal. The air pressure is a little above normal. That means there is more pressure. Are you getting it now? Pressure. The air pressure is a little below normal. You know, for compression to happen, you apply more force. Abi? For compression to happen, you apply what? More force. Abi? That's why there's more what? There's more pressure. That means the normal air pressure that is supposed to be within that object is a little above normal. Now, but refraction, there is lesser pressure. Are you getting it now? So it's a little below normal. So that's for compression and refraction. Then a typical example would be examples of longitudinal waves are examples of longitudinal waves. Examples of longitudinal waves. Yes, examples of longitudinal waves. One, we have waves in spring, just like we discussed now. Waves in spring. Waves in spring. 2, sound waves. Sound waves. Sound waves. Sound waves. Then 3, waves in pipe or tube. Waves in pipe or tube. Waves in pipe or tube. Waves in pipes or tubes. So this brings us to the end of classification of waves. Is there any question? Is there any question? Ask questions. We're not done with the class. Don't close your book. We're not done with the class. Rejoice. Open that book.
I did not close.
Thank you.
I did not close it now.
Open the book.
I'm fasting. Unless I let you go. I died. I died.
Is there any question so far?
When I go my one and come back next week, come and tell me the questions.
Alright. And I'll also be waiting for you to give you my own questions. Alright, the next aspect we'll be moving into is terms used in describing waves. Terms used in describing waves. Not terms as in the musician. Used in describing waves.
I'll give him now. I'll use this. Mr. Sage, please.
I lost it now.
The pen.
Terms used in describing waves. Hello. So the first one we're talking about is wave fronts. Wave front. Saba BMC.
Wavefront.
Yeah.
Are you watching this class? Do you know that there is a class on that?
This is any line or section this is any line or section through which a wave advances. Through which a wave what advances or moves in phase. Or moves in phase. You have something like this. These lines now it is spreading across. These lines at which it moves is the what? Is the wave front. This is any line or section through which a wave advances or moves in what? In phase. Number 2. We have amplitude. 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 Before this colon, put capital A and close bracket. It is denoted by capital letter A. This is the maximum displacement of the wave particles. This is the maximum displacement of the wave particle from its mean or rest position. From its mean or rest position. It is measured in meters. It is measured in what? In meters. It is measured in meters. So this is the amplitude. Highest displacement. Maximum displacement from its what? From its rest position. Then you measure it here. You trace it to this side. This is the what? Amplitude. It is usually measured in what? In meters. So the next one. Trace it to this side. The line must be showing. The dotted line must trace it to the other side. So the next one is the wavelength. Wavelength. The wavelength. Put in brackets lambda. 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 This is the distance. This is the distance. Lambda. Lambda. Between two successive wave crests or troughs.
Down the trough. Amplitude down.
This place.
Yes.
Why is this place? Why? Do you get that? So now, what from the definition of wavelength, what did you say it is? Distance between two successive wave crests or trough. So this from this part to this part is the what? Is the lambda. From this part to this part is the what? Is the lambda. That is what that definition is telling you. So this place, assuming we name this place point A and this place point B, then this part C and D. We can say point AB is equals what? CD. Is there any question? And they are all equals to what? Lambda. Is there any question? Is there any question? Is there any question? All right. AB, successive crests, CD, successive crests, and they are all equal to what? Lambda. The next one is frequency. Frequency. They are equated to lambda.
Hold on, please.
Yo. Frequency denote with what? Small f. Close the bracket. Denote with small f. This is the number of complete oscillations. This is the number of complete oscillations. This is the number of complete oscillations or cycle cycle as in CYCLE, not CIRCLE. Made by a wave in 1 second. Made by a wave in 1 second. Made by a wave in 1 second. And it is measured in what? It is measured in what? Thank you. Hertz. It is measured in. It is measured in what? In hertz. It is measured in hertz. What is this one trying to tell us? Yes? Now let's quickly take one simple question. Look at this. Hello. If it takes a wave 1 second to complete this, that's from point A to point B, from point A to point B. Okay. If it takes it 1 second to complete it, what is the frequency? Why is it 2? Thank you. It has 2 complete oscillations. Made in what? In 1 second. How is it 2 complete oscillations? From this part, we have half, then another what? Half. Full complete what? Oscillation. Having? Then from here again, another one. 1, 2. Are we together? So it is making what? 2 complete oscillations or what? Cycle. For it to make the crest and the trough, it has completed what? 1 complete what? Oscillation. Abi? 1 crest, 1 trough, complete what? Oscillation. Another crest, another trough. 2 complete what? Oscillations. Do you get that now? In what? In 1 second. So our frequency is what? Our frequency is what? 2 Hertz. Is there any question? Any question? All right. Let's move to the next one. Period. Period denotes with capital T. Denotes with what? Capital T. This is the time taken this is the time taken by a wave. This is the time taken by a wave to complete a cycle. This is the time taken by a wave to complete a cycle or make an oscillation. To complete a cycle or make an oscillation. Full stop. It is measured in in what? In seconds. It is measured in what? In seconds. Full stop. It is also the reverse of frequency. It is also the reverse of what? Of frequency. Therefore, you can say T is equals 1 over F. We'll discuss that. So she asked for formula for frequency. From what we can deduce here, we can say the formula for frequency is what? Number of oscillation or of complete cycle all over what? The time taken. The time what? Taken. So the time to complete that oscillation now is now the what? The period. So you can also say frequency is reverse of the what? Period. Do you get that? You see that they are what? Interwoven. So this can be number of oscillation over the what? Time taken, which is also 1 over. Is there any question?
So then, should we have frequency that's also velocity over wavelength?
Light is light. So the next one. So if we are to calculate the period for this same question, what would the period be? Yes?
T over N, time taken over number of.
C is equals 1 over 2, Abby, which is what? 0.5. Is it 0.5? So 0.5 seconds. So one complete oscillation will take what? 0.5 seconds. Two complete oscillation will take what? 1 second. Do you understand? Any question? Where's that SS1 boy? Wave speed. The next one we'll be talking about is wave speed. Hello? It's zone out. Wave speed. Wave speed. Wave speed. So denote the wave speed with what? It's V. This is the distance traveled. This is the distance traveled. This is the distance traveled by a wave per unit time. This is the distance traveled by a wave per unit time. And it is measured in meter per second. It is measured in what?
Meter per second.
So as we all know that our, what's the formula for speed? Speed. Speed is what? Distance over distance over time. What is now velocity? Thank you. Displacement over time taken. All right. Now, when we are talking about wave, the wave speed will be what? Yes, the wave speed. Among all the parameters we have been discussing since morning, which one correlates more with distance? Wavelength. Thank you. So we have wavelength. Which one correlates more with time? Over wave period. So we can say our wave speed is equals to wavelength over wave period, right? And this is denoted by what? Lambda over what? T. So we can say V is equals lambda over T. Now remember that T is also equals 1 over F. Having, therefore we can say V is equals F lambda. Any question? Any question? This is very direct. I've never started calculation. This is very, very what? Direct. So let's take one or two calculations. Let's take one or two calculations. Rejoice. Yeah. You solve number 1 for us. The first example. Put this question down. A radio wave of frequency. A radio wave of frequency. A radio wave of frequency. A radio wave of frequency 1.2 times 10 raised to power 3. 1.2 times 10 raised to power 3 megahertz. 1.2 times 10 raised to power 3 megahertz. 1.2 times 10 raised to power 3 megahertz. Alright. As a speed of what's the speed of the radio wave? Without me telling you, what's the speed? Thank you. Why? Thank you. Radio wave travels at the speed of light. Hello, madam. These are the students. No, she's not a student. She's not a student. So leave them. Let them answer. Let them what? Answer. So why are we using 3.0 times 10 raised to power 8? I'm not hearing you. It has the same speed as light. And why is that? Because it is electromagnetic in nature now. Alright, so a radio wave of frequency 1.2 times 10 raised to power 3 megahertz has a speed of 3.0 times 10 raised to power 8 meter per second. Full stop. Determine its wavelength. Yes. What formula are we using? What are the parameters given? we are given velocity and what?
Frequency.
Velocity is what? 3.0 times 10 raised to power 8 meter per second. Then frequency is what? 1.2 times 10 raised to power 3 what? Megahertz. Now what is mega? Convert to standard form. What is mega? 10 raised to power what? Assignment 2. Assignment 2. Assignment 2. Write out and memorize multiples and submultiples in physics. Multiples and submultiples in physics. And if we used to do data subscription, they tell you I'm 800 MB left. So you know that is megabyte. Okay, no problem. So that is assignment 2, multiples and submultiples in physics. All right, mega means 1 times 10 raised to power what? 1 times 10 raised to power 6. Abi.
Yes, sir.
Hey. So for frequency, our new frequency will be 1.2 times 10 raised to power 3 times 10 raised to power 6 Hz. Abi. And from your indices, what do you do here?
3 plus 6.
1.2 times 10 raised to power 3 plus 6 Hz. So our frequency is now 1.2 times 10 raised to power 9 Hz. Abi?
Yes.
So remember, what are we looking for?
Wavelengths.
We are looking for the wave length. We are looking for lambda. Lambda is unknown. And we have V. So V, what's the relationship between VF and lambda? What is the relationship between wave speed, wave frequency, and wavelength? Yes? Thank you. V is equals F lambda. So from here we can make lambda the subject of the formula. So divide both sides by what? By the frequency. So F cancel F. Our lambda is now equals V over F. So lambda is equals what? 3.0 times 10 raised to power 8 all over what? 1.2 times 10 raised to power 9. So lambda is equals what? Lambda is equals, punch your calculator. How many 1.2 can you see in 3.0? So we can see what? 2 point times 10 raised to power what? This one minus 1. So thank you. Lambda is equal to what? If you move the decimal, we have what? 0.25. Lambda is measured in what? Lambda is measured in what? Meters. So put 0.25 meters as our answer. Is there any question? Rejoice! Look at me. Ask your question so that you might rejoice later.
There's no question.
There's no question. Are you sure?
Someone just asked if we have this class every Sunday. So please respond to that.
Yes, we have this class every Sunday from 3 to 6. Just 3 hours class.
So another person said you should please repeat the question again.
Alright, the question goes thus. A radio wave of frequency 1.2 times 10 raised to power 3 megahertz. 1.2 times 10 raised to power 3 megahertz has a speed of 3.0 times 10 raised to power 8 meter per second. Full stop. Determine its wavelength. So this is the wavelength. Example 2. Example 2. Put down this question. Example 2. I'll go over the question twice. Example 2. 60 complete waves.
Someone said, "Sir, you are too fast."
Wow.
My
Wow.
response to that is, please, when the live class is off, you can watch it
Yes, you
again,
can watch it over
because
and
we'll
over again.
upload it.
So 60 complete waves. 60 complete waves. 60 complete waves passes a particular point. 60 complete waves. 60 complete waves passes a particular point. 60 complete waves passes a particular point. Passes a particular point in 1 minute. 60 complete waves passes a particular point in 1 minute, comma. If the distance, please take note, if the distance between 3 consecutive crests, if the distance between 3 consecutive crests of the wave, if the distance between 3 consecutive crests of the wave is 1.4 meters, is 1.4 meters. Full stop. Determine the following. Determine the following. Let me go over the question again. 60 complete wave passes a particular point in 1 minute. 60 complete wave passes a particular point in 1 minute. If the distance between 3 consecutive crests of the wave, if the distance between 3 consecutive crests of the wave is 1.4 meters, determine the following. 1. Frequency. 1. Frequency. 2. Period. 1. Frequency. 2. Period. 3. Wavelength. 3. Wavelength. 3. Wavelength. And 4. Wave speed. And 4. Wave speed. Determine the following. 1. Frequency. 2. Period. 3. Wavelength. 4. Wave speed. Yes, how do we go about that? What were the parameters given? What were the parameters given? Yes?
Lambda.
What is lambda now?
1.4.
Now, in this kind of question, you don't just drop down parameters. First thing you do, the first approach you give it is the diagram. You were given a question and they told you the distance between 3 consecutive crests. Will you calculate that in your brain? You have to put down what? A diagram. Do you get that now? That is the first approach. The first approach is what? The diagram. Then you draw it out. So between 3 consecutive crests is this. So this is the first crest, second crest, and what? Third crest. Abi? Now between the first crest and the second crest, what do we have?
Lambda.
Lambda. Then between this one and this one, what do we have again? Another what? Lambda. So this is what? this is what? Hello. Let's trace it down here and trace it down here. So the question is telling us between this and this is what? 1.4 meters. Definitely we can deduce that what? 2 lambda is equals to what? 1.4 meters. Abi? So let's remove this meter because we are still solving, so it won't look like algebraic equation. So we divide both sides by what? Divide both sides by 2. 2 here, 1, 1. So lambda is equals 2 here, 1, 2 here, 0.7. So we have 0.7 meter as our lambda. Any question? Now back to the question. What were we looking for? What's the first one?
Frequency.
Okay, what other parameters were we given? Number of complete waves. Number of complete oscillation. Oscillation is what? 60. Is 60. Abi? What else were we given?
Time.
What time?
1 minute.
1 minute. The time is what? 1 minute. And that time is what? Is that what I'm asking you? That time is what? What parameter is that time?
They gave us minutes. They gave us time. Minutes.
That parameter, that time is what? Is what parameter?
Period.
Thank you. It's period. Yes. It takes. What's the definition of a period again? Let's go back. Oh yeah. Open. I give you permission.
This
The
is the
time taken by a wave to complete a cycle or make an oscillation.
The time taken by a wave to complete an what?
A cycle.
A cycle or
Make an oscillation.
make an oscillation. Definitely, it takes what? 1 minute to complete what? 60 oscillations. Abi? So that will be what? 60 divided by what? By the 1 minute. Abi? Which is 60 seconds. That will give us the what? The period.
So like that time, the time period.
The time is not the period. So the time is actually indicating that the period is here. The period is here. Are you getting it now? So the time now, okay, the period now will now be what? Okay, let's do it like this. The frequency, what's the formula for the frequency again?
F equals to N over T.
F is equals to what? N over T. So number of oscillation is what? 60, having. And the time is what?
60 seconds.
Time is
1
1 minute, which is what?
60
60 seconds. So we can say 60 over 60. So this is what? 1 eighth. Having?
Yes.
Now that 1 eighth is same thing as what? 1 second. Because the period is what? Is 1 second. Because it takes 1 second to complete one what? Complete oscillation. Having to complete an oscillation. So 60 seconds, which is 1 minute, will create what? 60 complete oscillations. So remember, our period is our frequency is inverse of the period. So 1 over 1 is still 1. So our period is now what? 1 second. While our frequency is 1 hertz. What else are we looking for? The wavelength. The wavelength was given, Abi. We have gotten the wavelength from the beginning, Abi, which is was 0.7. Then what else are we looking for? Wave speed. Wave speed. The wave speed is what? V. Which is what?
F lambda.
Which
F
is
times
F lambda. What is F? 1. 1 times 0.7. So our wave speed is what?
0.7 meter per second.
0.7 meter per second. Is there any question? Rejoice! Is there any question?
Your name don't go viral.
You know Rejoice. You know Rejoice now.
It doesn't call interesting.
You know Rejoice. She knows Rejoice. Her name was not Rejoice, but I've seen the future that there's one Rejoice that is coming. So the Rejoice is here. Is there any question? Any question? Assignment. Assignment number. Assignment number. That's how we'll be taking assignments. So assignment now water for you.
Excuse me, sir. Someone said, please, can someone post the questions in the chat? Okay. Nobody can post the question in the chat, so we are sorry. So hopefully by next week, all the questions will be prepared so that we can post them in the chat. Okay. Someone said there are questions. Please, S. Munid, or what do you call yourself? Please ask your question. Type your question so that the teacher can respond.
Yes, you can drop your questions.
Drop your question
Just
in
drop
the
your questions
comments.
in the comment section. All right. This is where we'll be rounding up the class for today. I'll give you assignment number 3. These are just baby assignments. Just play with it when you get
Next
to.
week when I'll come prepared, I beg.
Use my
The distance. This is JAMB question 1996 question 37. 1996 question 37. JAMB question 1996 question 37. The distance between two successive crests of a water wave. The distance between two successive crests of a water wave is 1 meter.
Okay, sir. Someone said, please, sir, I don't understand how you got the period and wavelength also.
All right, let's quickly take that. If you have been following, during the introduction of waves, I said there are some terminologies used to describe wave particles. Out of those terminologies, we discussed the wavelength and the wave speed and other things. And also, during the classification of wave, we said there are some that are classified based on the direction of travel. Based on the direction of travel. The first one was the transverse wave, which has two distinct regions, which are the crest and the what? And the trough. So now the question said the distance between 3 successive crests is what? 1.4 meter. And between that 3 successive crests, we have what? 2 wavelengths, 2 complete wavelengths, which is what? 2 lambda. So you bring out this 2 lambda and equate it to the what? To the distance. That's why I matched them like this. So we have 2 lambda to be equals 1.4 meters. Divide both sides by 2. So 1.4 will give us 1.4 divided by 2 will give us 0.7. Then the period. From the definition of period.
Continue, sir.
From the definition of period I gave you, I said it is the time taken to complete one full oscillation. Abi?
Yes, sir.
So now we were given the time taken to complete the 60 oscillations to do what? 1 minute, which is equivalent to what? 60 seconds. And remember, I also gave you another formula that frequency is what? The number of oscillations over what? Time taken. And that is what? N over T. So we have 60 over 60, which is giving us 1 Hertz. Abi? Now, if the frequency is 1, definitely the period will be what? Will be 1, because frequency is inverse of period and vice versa. So that's how we got 1 second and 1 Hertz. So I hope you have gotten the question. So back to our final assignment for the day. Said question 37, JAMB question for the year 1996. We have the question as: the distance between two successive crests of a water wave is 1 meter. The distance between two successive crests of a water wave is 1 meter. If a particle on the surface of the water, if a particle on the surface of the water makes two complete vertical oscillations, in 1 second, full stop, in 1 second, full stop, calculate the speed of the wave. And it is as simple as that. Yes, let me add one more. Final toppings. You know, when you go and buy ice cream, they put cherry on top. So this one is just the cherry on top. You know, if you go and buy rice in Mama Put, they put fisi. So this one is the fisi to crown it up. So I'll be drawing a diagram. No, it's just the cherry on top. These questions are simple. I've never started wave equation. So this one is what? Is warm up. I'm just warming up. Yes. I'm warming up. Alright, so we have something like this. 1, 2, 3. Yeah. 1, 2, 3. So from this point to this point is 0.01. From this point to this point is 0.02. This is displacement. Displacement y in centimeter. So this point is 0, the resting point. Then this point is 0.1. This point is 0.2, and this is 0.3, and this is 0.4, and this is 0.5. So using the waveform above, question. Using the waveform above, determine 1 amplitude. These questions are very simple. Just play with it.
Okay, sir.
So period.
Don't comb that chemistry, that physics, you will.
frequency of the wave. And this is where we call it a day.
So finally, sir, someone said, please, can you explain how you are interpreting the question to the diagram step by step? Sir, using the question.
You have to
So
be
please,
You have to be here.
officially.
you have to be
officially,
here. That's number one. Number
next
two,
class.
you can watch how we interpreted the question step by step when we post complete video. You can watch it from the very beginning again. And someone said, it's nice to see you, Mr. Juwon. Happy New Year.
Happy New Year to you too.
God bless you.
God bless you.
Sir, there's no cast.
See you next week, same time.
Same time,
Sir,
same
no-
station.
no special-
Same time,
Same time, same
same
station.
station. We catch you next time. So the thing is,
Sir, no
every
cast.
Sunday we've decided to be having this class, and it is just for us to cover. It is just for us to cover a particular part of physics, which Mr. Juwon will be handling. He would have joined us throughout the entire period, but due to the nature of his current job, so he has made out time. He decided to create this special time for everyone. So those of you who are interested in joining the physical class, we have to discuss before you join. Nobody is permitted to just walk in anyhow. So please have that at the back of your mind. And for the online class, you can always join. It is free of charge. Next time you join, please do well to share this to your friends, share with your friends, and we'll catch at the very top. 370 is not too big for you. You
Yes.
can get there.
Yes.
Thank you. Bye.
Right.
Shut up, Rondo.
At least last year we recorded 98 over 100.